we are having second session on smart material and structures. Today our speaker is for second session is Dr. Syed, Director Research and Consultancy, Exposys Data Lab, Bangalore. Dr. Syed Basith Muzammil, he did PhD from Bangalore University, specialized in advanced materials processing. He started his service as project scientist in CSIR, National Aerospace Laboratories, Bangalore, from July 2011. Later, he joined HKBK College of Engineering, Bangalore, and worked as assistant professor. After that, he joined Dawa University, Ethiopia, as assistant professor and member, Research and Technology Transfer Commission. He worked in Dawa University from December 2015 to December 2018. Now he is presently serving as Director, Research and Consultation in Exposys, Data Labs and Material Consulting, Bangalore from August 2019. He published 7 research papers. His current research areas are nano-reinforced double-degree hybrid high-performance FRP composites, SMA-reinforced smart composites for self-structure healing and characterization of 3D printed FRP composites. It's our privilege today that Sir is given his valuable time and to share his knowledge and experience with us. I request you to kindly take over the session and start your session, sir.
Thank you so much.
Yes.
Thank you, Mr. Mayor and Sari, for giving us an opportunity to share our experience here. So I hope all the participants have got a very good sessions in previous 3 days, and you would have got a very good exposure towards recent trends and innovation as the theme enlightens on. So today, let us talk something about the smart materials and structure. These class of materials are advanced material classes. So that means when we see materials are conventionally being derived or conventionally being differentiated into metal-based metallic materials, polymeric materials, ceramic materials, and the composite materials. Now,
sorry, sir, for interruption.
Material,
sir, your video is
off.
Hello, sir. Sir, your video is off, sir. Your video is on off mode.
Okay. Do you want me?
Yes, sir.
Is
Thank
this
you,
visible now?
Yes, sir. Thank you. Visible.
Thank you. So that's what, as we were discussing about the materials. Materials are being generally, discriminated into the metallic, organic, and composite materials. So now, these smart materials are the different class of materials wherein the materials are being manipulated in the atomic level and crystalline level. So this manipulation is turning into a different class of materials which are going to give some kind of different behaviors which are not generally available in the metallic materials or polymeric materials of the conventional classes. So that's what we are going to learn about, like these smart materials are, how exactly it is being applicable and how exactly we have to characterize and understand the behavior of these materials, and why these materials are called as the smart materials. I'm sure that most of us are unaware of this class of materials, smart materials, because still these materials are more into research and investigations. So we can see in very few applications we can find in aerospace and satellite applications, space applications, we can find these smart materials. And moreover, if we see the shape memory alloys and different types of materials which you see here, so these materials are generally we are coming into these materials are coming to notice first. Now I'm going to cover these topics as you can see in this slides, that overview of the smart materials. So what this smart materials are and its functionality of these materials, like how exactly it functions, why it is called as a smart materials, and all those things. Next, research opportunities. So I'm basically concerning on the the aspiring researchers and the young innovators. These people are very much concerned about smart materials. What these smart materials? What is the further area of investigation in smart materials and structures? How it can be applied and how we can improve the functionality of these class of materials. So that's why we have to discuss more onto this research opportunities in smart materials and how exactly the investigation gaps can be bridged. Investigation gaps can be patched into these smart structures for the high level of applicability and all. Next, advanced characterizations. How exactly we can characterize, how we can improvise the functionality, how we can make this to be applicable in wide areas of applications. Because we cannot everywhere deploy these electronic materials. So these materials are somewhere working on the replacement of the electronic materials as sensors, transducers, actuators, and all. So these materials are working generally on on the replacement of this electrical and electronic materials. You can see. So we have to characterize this smart materials and how we can justify the behavioral characteristics of these materials in terms of the micrographs, in terms of the different mechanical perspectives and other physical stimuli applications and all. Next, what are the trends in smart materials and smart composites? How we can deploy the smart materials to make into the smart structures. So that can be very much useful for different applications. So let's try to know what exactly these smart materials are. Smart materials are the new class of materials that responds dramatically under the influence of physical stimuli. Physical stimuli may be the temperature, electricity, pressure, mechanical forces, light, magnetism, moisture, chemical influence, etc. So that means we can say it works. This class of materials, as we are categorizing, materials are changing its shape under the influence of temperature. So that means we can say when the temperature is getting increased, it is changing its shape and is memorizing that particular shape. And when again the temperature brings back to some other the train temperature, it is regaining back to its original shape. So that's quite interesting to understand how these materials are behaving. Similarly, if you are seeing this electrically, that means materials which changes its color under the electrical influence. That means you can say if any machine, especially we used to deal with the machines. If any machine is being grounded, and of course, when it is conducted with electricity, and simply we are not aware of it, and if you're going and touching, then we are going to experience some shocks. What if we have some kind of coating which shows that, which changes its color under the influence of electrical conduction? So when the electricity is conducted, it changes its color. Then we can understand, yes, of course, this is conducted and we have to do some kind of repair works and all. Then we can go for the further operations. Next, pressure. What happens when the pressure is being applied onto some materials? Whether the electricity is being produced or when the electricity is being supplied, then it gives the mechanical movement, that's mechanical strain, mechanical changing shapes. So that's how these materials are being worked. So when the light is being applied, then what kind of light, whether it is the the monochromatic light or polychromatic light, what kind of light is being influenced on that? And with that influence of the light, how exactly the material is behaving? What is the physical stimuli is going to affect onto the characteristic of that particular material? Magnetism, moisture, chemical influence, and all. So these are all the few things which are directly affecting on the material characteristics. So let's talk more onto this. And these materials are being used for sensing the change in physical stimuli, actuate the mechanism, control the devices or structures, damage detection and monitoring. That is structural health monitoring, structural health healing. So let's say an example, what exactly the structural health monitoring and structural health healing is. Let us say we are flying in a plane and due to some turbulence or due to some bird impact or some kind of like damage which has already, it has been initiated. So because of this turbulence, because of the extra forces encountered some kind of like damage and the crack is getting propagated, then how we can reduce that thing, how we can avoid the catastrophes, how we can avoid the accidents. We should have to have some kind of mechanism wherein it can sustain to that kind of catastrophe, at least till we land, at least till we take our aircraft to some safer place when we can save the lives. So that is what, there should be some mechanism, and these class of materials are going to play a key role in this kind of situations. So these are the new class of materials wherein still a lot of innovations are to be registered. So that's what we can say. And self-corrective, self-controlling, and self-healing. As I mentioned, the structural healing. So this is what the things which we are going to learn into, with the influence, with the function and the proper application of the smart materials. Optimum and effective shock absorption and damage arrest. Now let us see, take an example of an aircraft. If we see Boeing 787 Dreamliner, so if this airplane is flying, its takeoff or landing load will be somewhere around 600 to 750 tons, metric tons. So that's quite huge. So to sustain that kind of load, to make a proper damping, cushioning effect, we should have to design some kind of mechanical setup, some kind of mechanical system wherein it can sustain that kind of heavy loads to make it to avoid from catastrophe and accidents. So for going with that, we have to take some kind of the materials which acts accordingly under the influence of that acting load. Let's take another example. If we have designed a truck which will be supposed to carry some 10 megaton of load. If we are designing the suspension for that particular kind of system, then of course it will give you the optimum cushioning, optimum damping at full load condition, that is 10 megaton load condition, metric ton load condition. What happens if it is unloaded and it has to return back? It is emptied. Now suspension will not respond. Mechanical suspension, conventional suspension will not respond to it. That means it produces a lot of vibrations because of the road irregularities, potholes, humps and all. So to avoid that kind of things, we have to make some kind of system, some kind of damping system, which will give you the optimum cushioning effect for whether it is a zero load condition or the full load condition. So that means we have to go for some kind of mechanism, which is generally, we can say, to be influenced with the magnetorheological or electrorheological fluids. That means this class of fluids, MR fluids or ER fluids, changes its rheology, changes its viscosity under the influence of magnetism in case of MR fluids, or under the influence of electrical conductivity and in case of ER fluids, that is electrorheological fluids. So when we are influencing that kind of thing with the suspension or with the amplitude we are getting, with the deformation we're getting in that, but then with that influence, kind of magnetism is being, magnetism will be intensified, and because of that magnetism intensification, so this fluid will get solidified. You can say it increases, it enhances the viscosity. So under that kind of mechanism, we can enhance the cushioning effect. So that means as it is getting, the deform or making some kind of amplifications or in the moment, with that particular amplification, it gives that amount of cushioning effect. So whether it is a no load condition or full load condition, it will give a proper 100% secure damping characteristics we can achieve in that MR dampers. So this is the class of materials. Now generally listed materials are piezoelectric materials, shape memory alloys and polymers, MR or ER fluids, as I've told, magnetostrictive and electrostrictive materials, pH sensitive polymers, and the chromogenic systems. As I've told, the chromogenic systems are the materials or the coating. Usually it will be in the form of coatings or some kind of a layering thing, which gives it, which changes its color, that is chromogenic. It changes its color under the influence of the heat. Like you can say in some places, in some pizza delivery systems, advanced pizza delivery system, which I have seen in US, that when it is hot, sticker will change its color. There will be some sticker on it. So it changes its color. So that means when it is hot, color of the sticker will be different. When it is cold, that means if it is being delayed in delivery, it's obviously getting cold. So when it's getting cold, it changes its color. So that means without opening the box, we can see whether the pizza what we have inside is hot or cold. So that's that kind of things we can achieve with these chromogenic systems. So let's know what these piezoelectric materials are. Piezoelectric materials, we have we are known with this piezoelectric materials from our high school. That this class of materials, piezoelectric materials, are going to work under the influence of mechanical pressure and electrical impulses. Now we can say when electrical impulse is being given, when the electrical pulse is being given, it expands and contracts. So that means you can say when the electricity is being given, it makes some electrical mechanical strain. So it expands and contracts under the influence of electrical influence. So similarly, when we are giving electrical impulse, when we are giving electrical pulses onto this material, it expands and contracts. So that is what we can say. It works on whether we are giving the mechanical forces or stresses, it releases the electrical pulse, or when we are giving electrical pulses, it expands and contracts based on the terminal choosage. So that's what these piezoelectric ceramics or PZT, lead, zirconate, titanate materials are being used for several applications when we can deploy this for anti-icing applications in aircrafts, and we can deploy for the turbulence control applications in the smart skins and all. Now we can see here, in this, we can see like when the electrical, when it is being mechanically strained, when the stresses are being applied on this material, it releases the electrical pulses. Similarly, when it is being taken up into next level, now we can see how exactly the mechanical stresses are being stimulated for the generation of electrical pulses. So this can act like a sensor as well as an actuator. So sensor, when it is being influenced with the electrical conductivity, or when it is being influenced with mechanical stresses, then the electrical pulses will be produced. So these pulses can be taken as the input for that some particular processor, and then we can take a necessary action on that. Similarly, we can go for the electrical conductivity. When it is being influenced by the electrical conduction, then certainly it reduces its, it contracts and expands. So this mechanism can be used for making a kind of like bubbly effect onto the aircraft structures, which is generally being used in the smart skins of the aircrafts, advanced aircrafts, or combat aircrafts and all. Next, shape memory alloys. What these shape memory alloys are? Shape memory alloys are usually pseudo-elastic in nature. Now we can see it reacts in different way. One is the pseudo-elastic in nature, but it acts as the super elastic in nature. So that's what we can say. It's going to exhibit in two different ways. One is its own metallic behavior, and another is the shape memory effect into it. So for that, we have to understand the basics of this material sciences, that how exactly this martensitic and austenitic state works. Austenitic states are recrystallization state. We generally see this austenitic state in for forging and for hot rolling and for drawing and all, because we used to heat it to the red hot condition, recrystallization temperature, and then we are going to apply the mechanical forces to extract it out into some different shapes. So this is the real austenitic temperature level. So that is recrystallization stage of it. But these materials exhibits in two different ways. That means usually this alloys which have been found by NITINAL, that is Nickel Titanium Novel Ordnance Laboratory. And Novel Ordnance Laboratory has invented this with a combination of nickel and titanium alloy. So this NiTi alloy is also known as the NITINAL, so which is giving the utmost shape memory effect. So like that, CuAlNi, FeMnSi, CuZnL. So this class of materials are exhibiting this shape memory effect in it. So out of this NITINAL or NiTi alloys are going to give a maximum shape memory effect. So that's why it is widely being used commercially. We can see that. The shape memory effect is due to a change in crystalline structure, as I mentioned. It deforms and it memorizes the shape. Let us say, take an example of this pen. What happens when I'm trying to bend this? It will get bent, right? And when I'm releasing into it, it will not regain to its original position where it is plastically deformed. When it is plastically deformed, it will get bent, right? So now in this class of materials, what happens is when I'm bending this, and before bending, what I'm doing is this class of materials to be like first strain. I'm heating this to the real austenitic temperature, that is somewhere around 750 degrees Celsius. When I'm heating this to a 750 degrees Celsius, it memorizes the original shape. So that means the crystals are being arranged into that particular arrangement. So that means if I am leaving this straight beam condition will be its original condition. So that's what it memorizes. Now what I do is I'm going to deform it after making this cool. Now I'm going to deform it to some level, or I'm going to twist it. I'm going to apply some mechanical forces and I'm going to bend it. And what I do is, again, I'm going to subject it to some temperature change, maybe 30 or 40 degree temperature change to the room temperature. So that means room temperature will be somewhere around 25 to 30 degrees Celsius. And I'm increasing this to somewhere around 65 to 70 degrees Celsius. When I am dipping this into the water of 75 degrees Celsius, then it regains back to its original shape. That is, when I am bending, it will get bent. It will make some kind of sagging. And when I am dipping this, when I am exposing this to a 75 degrees Celsius, then it regains back to its original shape. So that's how we have to train the material under so many cyclings. So under so many cyclings, we have to train. And with that cycling, we have to make sure that whatsoever the shape you give here, if it is being very thin wire, then I'm going to wind it. I'm going to make a tie, I'm making a knot on this. I'm tying a knot. And then again, if I'm just dipping it to a 75 degrees Celsius water, then it again regains back to its original shape. So that is what the fantastic feature we are going to achieve in this kind of alloys. So let's say, take an example of this, the rim of this spectacle. When it is being twisted by some kids, then usually they used to play, and if they are being twisted, then certainly we can see that this is no more to be used. This is making some kind of dance, some kind of twists and all. So I cannot use it again. But if we are taking this nitrate-based rims, then all we have to do is just to dip it into the water of 60 or 75 degrees Celsius. It regains back to its original shape without even having a mark of any twist. So that's a fantastic feature we can see in this class of materials. How this occurs? Now we have to understand why these materials are behaving this way, how we can achieve these kind of things. So to understand this, the materials what we are using here, it has got a different interstitial and substitutional effect. So when the materials are exposed, exposed to some temperature, then certainly it arranges its crystalline structure. It arranges its crystal structure. So that memorizes its shape as this is the original shape. Now, what we have to do, we have to see this alloying elements what we have, whether it is copper, nickel, and titanium. If you're taking, then nickel and titanium are the atoms of that are making some kind of substitutional and interstitial arrangements. So with that substitutional and interstitial arrangement is making its crystalline structure to arrange in that systematic way, so that it can memorize that particular shape. And under the influence of that particular thermal agitation, so when it is thermally agitated, then it regains back to its original position. When it regains back to its original position, of course, in macroscopically, we can see it has regained back to its shape. So that's what it's all just a matter of changing the atomic positions. When the atomic positions are being changed, it regains back to its original shape. So that's what we are achieving in the shape memory alloys. So like that, we have the shape memory polymers as well. So these shape memory polymers are also going to behave in the same fashion. Major applications we can find in aircrafts for morphing of wings. Let's say if we have the load carrying aircraft, when it is producing the high torque, but speed will be less, because its structure, its aerodynamics are allowing it to carry more load, but speed we cannot expect. What if we have to achieve the more speed as well? We have to redesign its wings. When wings are being redesigned, then only we can manipulate in the speed and torque, with the speed and load carrying capacity. So in this thing, with the help of the shape memory alloys, we can deploy this shape memory alloys into a structure, into the wings, into the airfoils of it. What it happens, we are just training it to change its shape. So that makes this composite, smart composite, this composite of fiber reinforced composite, what we are using for the aircraft wings. So that will act as the fiber reinforced, smart composite. So because shape memory alloy wires are being embedded into it, these wires are being reinforced, double degree reinforced into it. So when these wires are being reinforced, then it changes its shape as we have trained earlier. So when we are training this, certainly it changes its shape. So because of it changing shape, what it happens is all we have to just do is in the air, we can change the geometry of the wings. When the geometry of the wings is being changed, when the wings goes back, when it changes its angle, the attack angle will be changed. And that's how we can increase the speed in the air. We need not to come down. We need not to land our aircraft to change its shape, change the shape of the wings. No, we can do in the air just with the influence of some thermal agitation onto the composites. So that's how we can achieve this in the aircraft. Now, second example is we are generally seeing that in the dental implantations and all. In dental surgeries and dental implantations, we are using the shape memory wires, wherein it's simply body temperature is agitating that particular wire to make the proper stresses on it. So that's how it contracts. As it contracts, as the teeth are getting inside to change the inclination of it, as the wire contracts, it makes the proper stresses on it, and proper force will be deployed on that. So that means you need not to go to every time you need not to go to the dentist for tightening the wire and all. So, or if you are just deploying that wire into it, then it will automatically makes it to carry that kind of load. So that means this is again another advantage in the dental implantations or dental surgical implantations and other things. So next we have the dental braces, as I've told, and next in the robotics. As you can see in the picture, we are using the wires which are making just contractions on it. When it contracts under the influence of some thermal load, of course we are using here. We are using some thermistors and some kind of like heat generation devices we are using here. So when the heat generation devices are being used, when it is being influenced with thermal loads, then certainly it contracts. When it contracts, this arm, or you can say the end effector, will be closing its finger points. So that's what the wire, but we are using the shape memory wire that can be used for making its movement in the fingers. So that's how, whether it is a humanoid or industrial robots we are using. So if it is a lightweight or the low, or the lightweight applications, then certainly we can go for this shape memory alloys or the wires we can use here for achieving the actuation into it. So that's what you can see. The hysteresis graph, what you can see here in the martensitic level. Let me explain what this martensitic level is. Martensite to martensite shape transformation. Martensite to martensite crystal transformation, you can say. So this is, firstly, we have known in the earlier metallic materials, whether it is the iron or something, we are forging, we are heating, we are doing rolling, drawing, all this we are doing after achieving it to the austenitic temperature level. Now, this martensite to martensite, as I have told, in the martensitic level, so that means there are two austenitic levels. One is the original or true austenitic level, as I have told, that is around 750 degrees Celsius. So that is a true austenitic level. So when we are heating the material to true austenitic level, though we have trained to some shape and all, when we are heating again to a 750 degrees Celsius, then it forgets its shape. So that is called as amnesia. So it completely forgets its shape. So crystals will be arranged to that particular level. So now we can say, if I have some wire and I have just twisted and put a knot, and then I'm hitting it to with the help of some flame or something, I'm hitting it to 750 degrees Celsius. Then what it happens? With that 750 degrees Celsius, it takes the crystals will be arranged to that particular shape. Atoms are arranged to that particular position. So that means under the influence of 750 degrees Celsius, it memorizes that particular shape. So now, if I am opening, I'm straightening the wire, and then if I am just subjecting it to 75 degrees Celsius or 60 degrees Celsius, then again it makes a knot. It makes a knot onto it. So that means it again regain to its particular position. So that is the knot or what we have tied. So that will be the original shape it is getting memorized into. So that's what the original true austenitic stage, and the low temperature state, that is within 0 to 100 degrees Celsius, what we are saying. So these are the martensitic state in general. But in shape memory effect, we have two stages. One is when we are applying the mechanical stresses, so that will be, that's room temperature, that is the martensitic state. And when we are subjecting it to the little high temperature level, that is around 60 to 75 degrees Celsius, as I mentioned. So when we are subjecting it to a recrystallization temperature, then it again regains to its origin position. So that is called as the austeniting state. So that is the temporary austeniting state. So as we are just turning into the material sciences or material, material engineering terminologies, these are the martensitic and austeniting states of a shape memory alloy, which we are generally going to achieve in the shape memory effect to 0 to 100 degrees Celsius. So we can train the materials to memorize the shape. We can train the material to regain its shape in two effects. So that means generally we have a two-way shape memory effect and one-way shape memory effect. As I have told, if we are just bending it and we are just subjecting it to 75 degrees Celsius of water, or simply if the flame is being given, then what it happens? It regains back to its original position. So that is one-way effect. What happens when it has to deal with the two different temperatures? Then it memorizes the two different shapes. So when it memorizes two different shapes under very cold condition, under the normal condition, and the heated condition, then we can say it is the two-way shape memory effect. Now we can say what this one-way shape memory effect is. As the picture shows here, let me just stop this. As you can see here, in this we have a wire which is going to, which is being trained to stay into the normal straight beam condition. Now this is martensitic low state, a lower temperature state, usually the room temperature, right? Now what we are doing, we are going to bend it. We are going to apply mechanical forces onto it. When we are applying mechanical forces, of course, it is in RT, room temperature only. Okay, what it happens? It retains that particular shape, that is plastically deformed. So we have deformed this plastically. So that means whatever the forces we have applied, whatever the deformation we have given to that particular beam, it has achieved to that particular level only. Now, what we are doing next, what we are going to expose this to some elevated temperature. What is that elevated temperature be? It's elevated some temperature be somewhere around 60 degrees Celsius to 75 degrees Celsius or somewhere. When we are giving, this is a temporary austeniting state, as I mentioned just now. Temporary austeniting state. So that means in general, this is all martensitic state only. 0 to 100 or 200 degrees Celsius is all just a martensitic state only. Because austeniting, real austeniting state is 750 degrees Celsius. Now, this shape memory austeniting state is somewhere around 60 to 75 degrees Celsius. So we are going to influence this deformed beam into the 75 degrees Celsius exposure. When we are agitating this thermally, then it regains back to its original position. So that means it changes its shape. As you can see, it is changing its shape. Layer by layer, it is changing. It's changing to its original position. So within seconds, it changes its to the original position. So that's what, when we are again keeping this down and bringing it back to room temperature, it remain as it is. So that means you can see it remain even in the martensitic state, that is 25 degrees Celsius, it remain as it is. So that is how the one-way shape memory effect works. Now this video will be helping you in knowing like how exactly this thing works. Now this is being deformed. Now we can see it's being deformed. When it is being deformed, of course, it remains deformed. This is the martensitic state. Now we are subjecting this to thermal agitation. See, now you can see when it is thermally agitated, it changes its shape. It brings back to the original position. Now let me play once again. Martensitic state, martensitic mechanical stressing state. Austeniting state, and when we are leaving, again it comes back to martensitic state. So this is how it works. This shape memory effect, one-way shape memory effect works. Now we can see, Now we can see here how exactly this temperature versus the strain works over here. So as the temperature increases, what happens here? It is making into the martensite and twin martensite state. So when we are applying mechanical stresses, now we can see the lower bottom figure is a twin martensite state. So that means we have trained that to particular shape. Now, when we are applying mechanical stresses, then it changes. So that means rearranged. Atoms and crystals are rearranged. Now, again, what we are doing, we are subjecting it to some elevated temperature. When we are making the thermal agitation, then it comes back to its original position. Now, again, we are cooling, crystals are arranged in that position. So that means the normal crystalline structure will become twin martensite state. Austenitic state, martensitic state, twin martensitic state we can achieve here. Now, two-way shape memory effect. So as I've told you, when it memorizes the two different shapes under two different temperature levels, then we can say it is the two-way shape memory effect of the materials. So for two-way shape memory effect, it should be very meticulously handled. So that means we can say, if we are understanding the two-way shape memory effect, and if we are giving the two different states of the temperature levels, or you can say the two different temperature levels we are giving, then it memorizes the two different shape states. Two different states it will be memorizing. So that's what we can see. A martensitic state, we are having some martensitic state, that is the original position. Now we have made into severe deformation. So when we have deformed it mechanically in the martensitic state as itself. Next, we are subjecting it to heated condition. So when we are subjecting to some heated level, maybe somewhere around 45 degrees Celsius, then it changes its shape to some level. It changes its shape to some level. And again, when it is being cooled, again to some, the very low temperatures and all, so then it regains another temperature, another position. So that's what we can say, when it memorizes the two different shapes at the same time. So the same pen can be used for the twisted condition in one way, or you can say it will be used for the bending condition in another way. So these two things can be achieved with the two-way shape memory effect. So we have to go for the very meticulously training of this particular materials for two-way shape memory effects. Now you can see this videos which shows like inchworm motor, how exactly this inchworm motor works. Or you can see this is memorizing and it comes to the one position, and when it is being cooled again, see, it memorizes another position. So that means the mechanical deformation, the severe deformation what we have achieved will be expressing its two different shapes into it. So that is heated water. We can see in the heated water, it memorizes one shape, and when it is bringing back to a room temperature, it memorizes another shape. You can clearly see here. I play once again, you can see. This is mechanical. See, this is severe deformation. So that means we have deformed with the mechanical forces, of course. Now we are just heating it to some temperature with the heated water. You can see. See, it memorizes one shape. So it brings to one shape. You can see here. Just a moment. And again, it memorizes to another shape. Similarly, you can see inchworm motor, how exactly it works here. So that means it is memorizing the two different shapes. So these two shapes, like expanding, contracting, expanding, contracting, expanding, contracting. So this is how the two-way shape memory effect works. So these are the simple examples, like how exactly this crystalline structure works in achieving the mechanical deformations. So these mechanical deformations can be used for any kind of actuations. So that's what the benefits of two-way shape memory, shape memory alloys. Now coming to MR fluids. These MR fluids are, that is magnetological fluids, are the non-Newtonian fluids, because it is not going to express its Newtonian characteristics. It's not going to give the constant viscosity under the influence of so-and-so shear forces and all. So this is how we can see when the material is going to exhibit. So that means the suspended material, this is in the liquid state. When the ferromagnetic particles are being suspended in the silicon oil with some additives, it is in the liquid state. And when the magnetic field is being intensified around it, it changes its viscosity. So that means the suspension of the magnetic particles, what you have, magnetic particles will be in the micron size or nano level. So these magnetic particles, what you have, if this arranges in a systematic way, when in the silicon oil will be packed within the particle layers. silicon oil will be packed within the particle layers. So then it gives a kind of like cushioning effect, isn't it? So that is how this cushioning effect in macroscopically, it will be showing you like a change in viscosity, change in rheology. So that is why these materials are called as magnetorheological fluids. So now we can see in this picture, like when the magnetic field is being applied onto the material, onto the some system, when in the ferromagnetic particles are suspended into silicon oil, which is generally in like a black liquid kind of color. So it's just like in a liquid state. When the magnetic field is being applied, it solidifies. That means you can say it's not solidifying, but it's mechanically getting, influenced like a, a kind of like wall it is building. With the fluxes, what you have magnetic fluxes, under the influence of that magnetic fluxes, it is building up the walls like this. And within these walls, the silicon oil is there. And suppose if you're applying some mechanical loads onto it, then it acts like a cushioning effect, because oil is suspended, oil is there, and magnetic particles which were freely suspended have made a kind of wall onto this. So that is how it gives you the cushioning effect into it. So that's what these MR fluids can be the best dampers. This can be used to prepare the best class of dampers, which are generally being used for the commercial aircrafts, the military aircrafts, and sports cars like Ferrari, Lamborghinis, and all the sports cars, Formula cars, and all. We are using this kind of suspensions onto it. We are going to use this kind of dampers. So I hope the MR fluid concept you have understood. So now we can see, like as the magnetic intensity is increased, you can say the strength of this wall will be enhanced. When the strength of this wall is enhanced, it resists that kind of like forces. So when the mechanical forces are being applied, then it resists that kind of thing. So that means as it strengthens, as the magnetic field is being strengthened, then obviously it makes a stronger wall. When it makes a stronger wall, then it does not allow any kind of like mechanical action. That means it offers that optimum amount of the resistance against it. So that's how, as magnetic field is getting increased, it gives you that kind of like resistance against it. So that's what we can say. It is not limited to the compressible fluid dampers and other things, air dampers, compressible fluid dampers, and other suspension types. This will be still effective type of dampers we can build with the help of this MR fluids. So that's what we can achieve. Let us take an example, one more thing. I've got just one thing in my mind, in my brain. So that you can say, if this is filled with, if let us say, what you can say, okay, let me just take this example. If this is filled with MR fluid and has got a piston in it, right, as the damper it has, so it has got a piston effect. And here we have our chassis or whatever we have here. The load application will be on above. Now let us see, if there is full load condition, it gives maximum compression. When it gives maximum compression, suppose let us see, we have here a rheostat is attached with it, which is having electrical conductivity, of course. When it is getting reduced, that rheostat level is getting reduced, then resistance will be reduced. Electrical resistance will be reduced. When electrical resistance is reduced, electrical conductivity will increase. With that electrical conductivity, magnetic fluxes will be enhanced on that. Based on the intensity of the electricity we have, the intensity of magnetism can be achieved on it. So when this magnetism intensity can be achieved with the decrease in this level, that means you can say, as the piston level goes down, there should be a mechanism in taking down this rheostat level, resistance level. Then the conductivity will be increased, and because with that electrical conductivity, magnetic field will be strengthened. When the magnetic field is strengthening, then that kind of like a stronger wall will be generated, and with that stronger wall, it acts like more stronger. That means it offers more resistance against the acting load. So that's how, whether it is a zero loaded condition or the fully loaded condition, this strut offers the optimum damping effect into it. So that's how this magnetic fluid, MR fluid works. Similarly, electrorheological fluids are there. So many electrorheological fluids are there. So in that electrorheological fluids, those fluids are also acting in the same way when it is being influenced with the electricity, not with magnetism. The same concept, but only the fluid things will be changed and physical stimuli will be changed. So that's what magnetism has been replaced with the electricity. Now, magnetic shape memory alloys. So we got to know that shape memory alloys, right? Magnetic shape memory alloys are some other type of alloys wherein it memorizes its shapes under the influence of magnetism. So that means we are not using temperature here. We are using magnetism here. So this single crystalline, that is nickel, magnesium, gallium alloys or magnetic shape memory alloys, MSM alloys, it's also being known. So these alloys are going to exhibit a different kind of characteristic. So that is generally being worked, it's going to function in a similar fashion as the shape memory alloy works, but the extra physical stimuli we are using as magnetism here. So as we know, magnetism, it's again changes its crystalline structure. So under the influence of the magnetism, which makes the polarization of it. So that polarization can be changed, can be used for changing its shape under the very thin sections. That's wire and very thin wire, thin stripes and all. So we can use that kind of things. So that's how martensitic, as we were using for the shape memory alloys, martensitic and austenitic state. So this is also we are using as the martensitic state only. That is the no magnetism level. When this being magnetized, then it changes its shape. That's called as again the austenitic state. What we are referring into the normal SMA shape memory alloys. So these are being used in this class of materials are being changed its shape onto that. Next, pH sensitive polymers. What is pH sensitive polymers? As we all know that this class of material, these polymers are getting swallowed and collapsed under the influence of pH level. So suppose if we have the pH level which is varying from 10 to 1, okay, which is varying from 1 to 10. So when it is being the pH sensitive polymers what we have here, we are using a special class of the swallowing gels here. So these gels are being swallowed under the influence of acidic influence also. When the acidic influence is more, it's getting swallowed. And when acidic influence is below the level, below the required level, it collapses. That's what it says. When it is being suspended into some particular material, I mean, when it is being influenced with some part of like acidic influence, then certainly we can understand that this is showing this kind of like acidic influence on this. So as the pH paper works, these polymers are working on the same way. So this can be used for several applications, like in petroleum industries, chemical industries, pharmaceutical industries, to justify and to know the pH level and to stabilize the pH level of different medicines and chemicals. Halochromic materials. As I have told you, the chromogenic materials. Chromogenic materials are the materials which change its color with the influence of the temperature, with the influence of electricity, with the influence of acidic influence and other things. So that's what we can say. Halochromic materials are commonly materials that arranges their color as a result of change in acidity. Halochromic materials are with the change in acidity, we are going to experience a change in color. And like that, we have the thermochromic materials also, which change its color based on the thermal changes. That is thermal change. When it is being influenced with the thermal change, then you can say color is getting changed onto it. So that's what you can see in the pictures. The visual thermochromism that you can see for 70 degrees Celsius, it's a little darker. For 80 degrees Celsius, it's a little lighter. So in that way, we can say as it's getting cooled down, the color becomes darker. And as it is getting heated up, color will be very lighter. So that's what you can see for the different perspectives and applications wherein we need not to go and check with manual inspection is not needed. Only visual inspection could be enough to justify the acidic influence, or you can say to justify the electrical conductivity, or justify the this acidic influence or temperatures and all. So that's what you can say. Now, next, coming to a second topic. So this is all the brief about the smart materials, so which are going to be used in different perspectives for different applications. And we understood how exactly this smart materials functions. Few materials we have just discussed about, because if you are going to talk about the smart materials, even the whole day is not sufficient, because it's about a different categories of materials and different behaviors now. So if we have to just narrow our discussion so we can focus on to the research trends and how we can use it for the different applications and other things. Now coming to the next thing, that is research opportunities and investigation gaps in smart materials. So how we can initiate? Now we can see the aspiring researchers. Now we see composite is almost, the research and development in composite is almost, it has reached to its peak level. So we need now to do more investigations onto the single degree hybridizations or the compositions of with the fibers or with the metallic compositions with different substitutions, different reinforcements and all. We need not to do, because already a lot of research has already been achieved. So the new aspiring researchers or research scholars can go into the smart materials, how to characterize the smart materials, how to develop the new class of materials, how to improve its functionality, how to go for the better applicability, how to build up the devices. So all these things are very important in research and development, whether it is a fundamental research or applied research. So shape memory alloys I focus because it has most promising in the research trends right now we are doing with the help of shape memory alloys. So these are most promising because it shows the martensitic to martensitic transformation in shape without much change in temperature. We need not to change the temperature to the very high level. All we need to change is just from 20 degree to 30 degree difference. That's it. We need not to deal with very high temperatures or very low temperatures and all. So with just a little amount of temperature change can bring you to the best class of shape change into it. So that's why shape memory alloys and piezoelectric materials are most promising into it. So let's focus more on the shape memory alloys, as I am also very much interested, and this is also one of the areas of interest of me. So this is going to exhibit a different, the shapes with the temperature influence when these materials are properly trained and when these materials are being embedded into some structures. Let's say composites. We are using fiber reinforced composites, right? We are using the different class of fibers, high modulus fibers or low modulus fibers we are using, natural fibers or synthetic fibers, whatever be it. If you are using in between the layer of the fibers, if you are using the shape memory wires or shape memory meshes, which is already trained to change shape, then it gives you a change in structure at all. So that means the composite laminate itself can change its shape under the influence of this temperature changes in it. So we can say this has got a very much interesting areas in space, satellites, aerospace, and naval applications for changing its shapes, rudders, flaps, and automatic door opening and closing of the satellites, and antennas opening and closing, and the movement in the solar panels of the satellites. All these things can be achieved with the help of this shape memory alloys into it. Shape memory alloys can be used in flight dynamics, or the movement in the flaps, rudders, ailerons, etc. as I've told. So this can be used for the morphing of wings. Morphing of wings means a change in the shape of the wings, change in the aerodynamics with the change in shape of the wings. So that also can be possible with the help of this. Of course, the research has been done, and we have achieved this aerodynamics, morphing, and all these things in the micro aerial vehicles and unmanned aerial vehicles. But it has not brought to the higher level for the commercial aircrafts and the military aircrafts and all, because we need to do a lot of still manipulations, investigations and all, and then we can come to that conclusions and more applicability on it and more functionality on it. Automatic door opening, that's what antenna have told, and twist in helicopter blades. Now let us see, we have a different mechanism in twist in helicopter blades. So we have to go for a lot of linkages into it, whether to make change the angle of attack of the helicopter blades, or whether to make a further movements in the forward, backward, or stationary, or whatever it is. So we can use the change in airfoil. You can do change in the twist in the helicopter blades can be achieved with the help of this SMA reinforced carbon fiber reinforced polymers. In SMA reinforced CFRP composites, we can achieve all these things because most of the blades are being made by carbon fibers only. So that's why all we have to do is just to use this SMA into it. When we are using, of course, we can achieve a lot of things into it. So that's what A lot of dynamics can be achieved. We need not to go for any kind of like actuating mechanisms into it. But just by using these materials, we can achieve distinct actuation mechanisms we can achieve into it. Smart composites in aircraft wings. Orthopedic implantation in hip replacement, in knee replacements, and the bone replacements and all in orthopedic implantations, we can use the shape memory alloys. Of course, the titanium is the most adaptable, biocompatible material. So we can use, even the nickel is more compatible into it. So that's why it enhances the biocompatibility in it. So that's why we can use it for the more of the, as the bone is getting developed, as it the bone structure is getting developed, it can contract by more body temperature itself. So as the body temperature enhances, it contracts also. So that allows the material to contract or expands based on the requirement of the human body or bone structures. So it is more biocompatible as well. So that is why it can be used for the orthopedic implantation. Of course, it's being used for the smaller applications, for the stents into cardiovascular or some other places. We are using the stents. So these stents are also made by this nitinols or nickel titanium based alloys, which is going to change with the thermal agitation. It expands and curves the generates a bypass for the easy flow of blood in the cardiovascular applications. Yeah. One more thing is this composite structures with shape memory alloys embedded into it. That means SMA reinforced CFRP composites. Let's take an example. Let's see this structural healing. Structural healing mechanism can be achieved into it. How? When we are having the suspended wires, SMA wires into the CFRP composite, then when it influences with some kind of fiber damage and structural damage, which leads to the catastrophic damage under flight because of the so many air turbulences and all. So in that cases, what it happens is it makes it to memorize if some kind of like crack nucleation has been taken or some kind of like fiber damage has been taken. That fiber damage can make it to the crack propagation and then catastrophic failure of that particular structure. Maybe the wings, fuselages, ailerons, rudders, maybe whatever it is. So in that cases, especially wings are going to experience that kind of things. We need not to do any kind of mechanisms. As we see here, as the crack is being initiated here, let us see, crack is initiated here in the upper part of this particular pen. Then what happens when we are applying the mechanical forces like this? What happens when the crack is initiated here? When we are applying mechanical forces here, or let's say tensile forces are being acted, then what happens? This crack is going to expand. The crack will propagate and expand. When the crack is already taken a birth, and we are applying the mechanical forces like this or like this, then what happens? It simply cut off and makes it to the catastrophic failure. So that's what we can see here. But what happens when the crack is already taken up here and we are applying the upward forces here? Crack is initiated here. When we apply forces here or some compressive forces are being applied, then there is no chance of crack propagation. So that's how we can stop crack propagation on this. I think you understood, right? So that's what we see. When the crack is already taken a birth, then we have to go for some mechanisms like we have to apply this kind of loads. Suppose if we are having the SMA wires which are being embedded into it, and we have trained it to make it to in this kind of shape, then what happens when the crack is generated with the help of carbon fibers which are conductive in nature? This master computer will reveal in the aircraft that so and so places has encountered with some kind of crack and is expanding. So in that case, what happens? We are going to subject it to some heat with the help of some heating mechanism. And when we are heating, it closes the gap. It closes the gap of the crack and it applies this kind of mechanism. When applies, it compresses the crack growth, then the crack growth will be restricted. That's how we can safely land. So this is one of the greatest mechanisms we can achieve with the help of the shape memory alloys that can be suspended into some CFRP composites and all. And we can go for the further characterizations, whether it is in the form of the fatigue, whether it is in the form of the creep, or whether it is in the form of the bending, 3-point bending, or tension and compression. Because all we know that the wings are going to influence a lot of bending. That is, it acts like a 3-point bending. The fuselage will be acting as a downward load, and the lift forces will be acting into as the support, or you can say lifting force will be acting that way. So that's why the hinges of the aircraft, the cutting, hinges of the aircraft from fuselage, hinges of the wings with the fuselage are influenced with so much of stresses. That means the stress concentration will be more there. So in that cases and all, we can go for this kind of mechanisms just to stop at least for some time, so that the lives can be saved, so that we can avoid the catastrophic failures. So this is how the structural health monitoring and structural health healing can be achieved with the help of SMAs. Similarly, piezoelectric materials, PZTs, or PZTs can be used, that lead, zirconate, and titanate, that can be used for anti-icing in aircrafts. Now we see here anti-icing, ice deposition on the aircraft wings and the rudders and flaps and all is a common phenomenon, but it is being influenced with the colder regions and at the upper altitudes and all. When it has to move through the marshes or colder regions, then ice get deposits, and ice has got a tendency to agglomerate. Ice particles has got a tendency to agglomerate and make it to be a very stiffer structure onto it. When it becomes stiffer, then it is difficult to make any movement in the flaps, rudders, and all. So when it jams, then what happens? It's difficult to make a banking. It's difficult to make a turns, and it leads to a lot of moisture absorption as well. You can see this CFRP composites or any fiber reinforced composites has more tendency to absorb moisture. So these are all the things are there, which makes the structural damage and catastrophic failures and all. So for avoiding that thing, we have to have some mechanism for removing the ice into it. We cannot, of course, we cannot go for the wiping mechanism as we used to do for the windshields and all. We cannot wipe it because the forces are very high. So all we have to do is anti-icing mechanism. When ice get deposited, then certainly we'll come to know that sensors are sensing that there is some ice deposition. When there is some ice deposition, we have to make the ice to break and to slide down. To make the ice slide, what we have to do? When the ice is jammed, when the water is jammed completely, then it is difficult to take it off. How we have to do? We have to go to our refrigerator and we have to see in our freezer what happens when the ice cubes are being jammed in the tray. We have to twist it. When we twist it, then only it will break. We cannot hit it. We cannot make any mechanism. We cannot remove it all because it's completely agglomerated. It's become very stiff. So all we have to do is we have to make a little twist, then it cracks and slides out. So the same mechanism we can achieve in the structures with the help of this thing, that all these piezoelectric transducers are being mounted onto an aircraft structure, wherein what it happens is it will be in the normal state, and when some electrical pulses are being given, it expands. It creates a kind of bubbly structure. When it bubbles up, it generates a crack onto the ice. When it generates a crack, that's enough to slide it out. So that's how these kind of mechanisms are being achieved with the help of piezoelectric transducers. Next, surface coating. If you have to achieve this, hydrophobic coatings, and we have to go for anti-dust coatings and all, we can achieve with the help of these materials. Surface coating, as I've told, by using thermal or plasma coatings or conventional ways of thermal barrier coatings and all, we can go for the several coatings on the structures, maybe the metallic structures or composite structures or whatever. We can achieve different characteristics out of it. In case of the materials in the steam turbines and in power plants and all, we can go for the several chromogenic material. Chromogenic coatings like halochromic or thermochromic coatings you can see, and of course the electrochromic can be used for checking in whether the system has grounded and it has being conducted also, we can see, and we can avoid the accidents and all. So that's what these materials can be used. MRER fluids, as I've taken an example, that how this magnetorheological or electrorheological fluids can be used for making a dampers, and in other applications for making so many linkages or other mechanisms and all, we can go for these MR and ER fluids. So that will be more helpful in making some kind of like advanced mechanisms into it, which will be more functional, more adaptable to it. Nanocoating onto structures to achieve hydrophobic and dust repellent surfaces, as I've told. Fire retardant polymers, conductive polymers, and polymer matrix composites for online structural health monitoring and crack killing structures, as it's already mentioned. Nano-coated biocomposite alloys for animal body implantations. Whether that is a human or animal body implantations, we can go for the nano-coated biocompatible alloys. Let's see, if you're going for the carbon nanotubes or carbon, nanomaterials, which may not be, since they are like chemically synthesized, will make some kind of reaction with the human tissues, with the body tissues, in human or animal body tissues. So how we have to achieve a mechanism so that it can be more biocompatible? We can go for, if we want to enhance the hardness of some, the knee replacement or so. If you're making some knee, it will be like undergoing with the tribological distortions, right? Because of the body weight and because of the movements, it goes into the wear and tear. So that is tribological distortions. So tribological distortions can be avoided when the surface is harder. Suppose if you're using any implant and its life is somewhere around 11 years, 10 to 11 years, that is the maximum life we are achieving in any kind of like implant. So if we can enhance the implant durability to 25 years, then we can say in the life, there's no need of like further surgeries. There's no need of further implantations. There's no need of replacement of the implants. So that's how we can achieve with the nano coatings on it. So with the nano coatings, we have to achieve the harder surfaces, which will be tribologically sustainable. Now, how to achieve that? The nanomaterials are again being reactive to the human tissues. So for that, we have to go for the coating to the nano particles. For the coating, that is electrocoating, electroplating could be done. That is nickel electrocoating, nickel electroplating could be done for the carbon nanotubes for making it more compatible, and it offers the both properties of the nanomaterials what is being offered. That is mechanically or compatibly. Compatibility can be achieved with the nickel coating, and the nano characteristics can be achieved with the nanomaterials. So that's how we can achieve these kind of things, and we can deploy for examining the biocompatibility and mechanical sustainability, and we can see we can justify the durability of that particular implants into the human body. So drug delivery systems, high performance and economical drug delivery systems. With the more research and advancements is being done in the SME, then more there are more economical ways of achieving to that particular stance and different mechanisms. Wherein earlier you can say just 5 years ago, it was costing somewhere around 3 lakhs. Just a 5 mm or 10 mm stent was costing around 5 lakhs. Nowadays, it's being achieved for 70 to 80,000. Now you can say how it is being happened. This is not a magic. More research and development, more research and advancements is going on. So that's how with that research and advancement, more productivity is going on. And because of that, the economy is, it will be available in the economical prices and all. So that's how more advancements can be helpful in, making cheaper devices to be built up. Next, characterization of smart materials and alloys. How the characterization could be done? It's really difficult because it's not as simple as we do for the different alloys and the metals, because we are not just going to study about the crystalline structure, we are not going to study only about the compositions and all. We are not just going to study about the granular, grain boundaries and granular structures and all. No, it's all about understanding the atomic level and atomic arrangements, how the material behaves in different levels, different stages. Suppose let's take an example of the shape memory alloys, because it's most promising alloys. So that's why I'm just stressing more onto SMA, shape memory alloys. So in shape memory alloys, as I told that there is some interstitial C and substitutional effect, which is making it to arrange into different levels. If we see very closely, if you have to justify your outcomes, your theory, then how you will do it? You have to go for the ultra, high level of scannings, high level of electron scannings. So then only you can justify that, yes, this is how the atomic structure is influencing onto the material, and that is the reason it is getting agitated with the thermal agitation, and that results in a change in shape, and that is how it is memorizing its shape and all. So that's what we can achieve. And the different configurations, different the granular structures and the grain formations and different interstitials can be achieved with electron backscattered diffraction. So this is one of the setups, attachments in the scanning electron microscope we can generally see, which gives you the color contours in that, how exactly the surface characterization could be done. Now, second point is, of course, we were doing from a decade that surface characterization we are doing in different aspects, different, the positions and all we are doing. We are studying the surface characterizations now. But we have not lasted into a surface characterization, that is the two-dimensional surface characterization. Now, we have to understand how exactly it behaves underneath. How? That means you can say, if you are seeing just the structure, two-dimensional graph, you can see the micrograph. But when it is taken up into one layer and when we are studying another, then it's second graph on it. There should be some relation, right? Because grain boundaries are not only two-dimensional, grain boundaries are in three-dimensional. We should understand how these materials are going to react into it. So that is why to understand these things, we have to go for a three-dimensional graphing, micrographing of it. So then we can understand how exactly this boundary formation forms. So for doing that, all we have to do is the surface-to-surface characterizations and multiple scannings on it. Let's say if we have scanned this surface, then we have to mill it, which can be achieved by focused ion beam milling. With the help of focused ion beam milling, we are removing somewhere around 100 nanos layer. And after taking so many scans, we have removed to 100 nanometer layer. And then again, we are taking some scannings on it. And again, after taking 3-4 scannings, then again, we are removing it to the 100 nanometer layer. And again, we are scanning. So that's how the stage by stage scanning, which leads to somewhere around 30 or 40 scannings, 30 or 40 removal of material and scanning, that leads to build up a three-dimensional picture, three-dimensional micrograph, which will lead you to understand how exactly this crystalline structure and how exactly this granular structure forms. And we can justify into, like, with the help of what physical stimuli, how exactly this material behaves. We can study in deeper that what will be the material thermodynamics, how exactly the mechanical exposure of this particular material, and what happens under the what happens to this material under the mechanical stresses, and the mechanical strain, and the thermal stresses, and the electrical influences, and the magnetism, and so on and so things. We can study very deeply into it. We need not to go and do all this reinvention of the wheels like that. We need not to go and inspect and do experimentation on every point of time. All we can do is, with the different conceptual knowledge, we can understand, we can characterize it into a very, meticulously, very in a deeper way, we can understand how these materials can react onto a different physical stimuli. So that's what, we need not to go for the mechanical testings, we need not to go for the electrical testings, magnetic testings on it. All we can just achieve with the help of the previous data and previous investigations, we can achieve this kind of micrograph will show that material is behaving so and so in so and so way with that particular physical stimuli. So that's what we can achieve. That's what the two-dimensional EBSD we have already seen. Now this is a time for going for the three-dimensional reconstructions with the help of FIB, that's focused ion beam milling. We can achieve this one. This is the two-dimensional EBSD graph. So here we have a composition of aluminum, that is which is acting as the matrix, and HFAL3 that's acting as the reinforcements. Now we can see here this is making the picture, the patches in different colors, which makes which shows that the densification of the aluminum and where exactly, how exactly it's being dispersed, how exactly it's making kind of like interstitials is and substitutional effect of HFAL3 into the material. So this can show that is it's very dispersed way we can see in this HFAL3 in the picture 1, and here in the picture 2 also we can see it's like it's deposited in the randomly. So what happens if we are controlling that to make into proper uniformly dispersed, or it should get deposited in some particular patches and all. Whether it will enhances the electrical conductivity, whether it will offer the more magnetism, or whether it is going to be insulating on that particular level. So we can understand that on different stages of the the particular material in the macroscopic level, how exactly it behaves. If it is being conducted in that particular point to another particular point, if it is being taken from one point to other point. Here the electrical conductivity will be different, here it will be different. Here the magnetism will be different, here the magnetism will be different. Because of we are using so many materials. This is not a pure metal. This is of course the alloying of it. So that's what we can use, and we can manipulate, we can hybridize to the required level, wherein we can use it very effectively for the different applications. So that's what we can say. Another SEM graph here, which gives you the matrix and reinforcement things. And here you have the graph's color contour shows like how the reinforcement has been deposited onto a surface. We can just see here the grain sizes with the area fraction. We can just notify here. We can see very clearly here. So that's what the color contour shows, like the intensity of the deposition of the reinforcement onto a surface and all. You can see, and whatever the volume that's being adopted in that particular 2D graph. So this 2D graph, whatever the volume, whatever the spaces, whatever the area that's being occupied by this reinforcement element and matrix elements, we can generally see, and we can examine in the 2-dimensional graphs. But in 3-dimensional graphs, we can understand the exact formation of the grain boundaries, exact formation of the crystalline structure in all 3 dimensions, not in 2 dimensions. So that is what the true images can be developed with the slicing of the multiple slicing and capturing of the images in different levels. So that's what. So the 2-dimensional pictures, what you have seen here. Now you can see this is the 2-dimensional pictures which we are all like habitual of taking, which are all already we are experienced in examining this kind of pictures. But with the building up of layer by layer examinations, by removing the one layer with a FIB that's focused on the milling, and again capturing the second layer, and again after capturing second layer, again milling, again capturing the third layer, again milling, again capturing 4, 5, 6, 7, 8. Like that, we are going to take tens of layers of the image to form one 3-dimensional picture. So that's how it will be more helpful in understanding, characterizing, and making it more understandable for the different physical stimulus. Whether it will be more reactive to the thermal influence or magnetic influence or any kind of electrical influence or whatever it is. So we can understand. Even in the mechanical formations, like how strong it will be in tension, compression, and other ways, we can examine into different aspects of it. So that's how the 3-dimensional characterization could be very much helpful in the further course of examinations in fractographics or the micrographics more. Research trends and smart material. The final topic we have here is research trends and smart material. Sorry, I think it's the lecture is prolonged, increased.
Dr. Basith, if you conclude in maybe 5-10 minutes, I think it will be better, because maybe audience
I'll try to conclude in another 10 minutes, sir.
After the question answer session
sorry,
is there,
actually, I am seeing the clock now. It has prolonged. Anyways, the trends in smart materials we can see here, like shared memory alloys, notably as I told you, nickel titanium wires can be used for as a secondary reinforcement in the composites, the FRP composites, and can be used as the the smart composite for the flexural and fatigue damage, to avoid the flexural and fatigue damage, as I've already taken an example, like how it can be helpful in different loading conditions and how it can be responding in to that particular conditions and all. Enhancement of the structural life, that is using SMA in the hygrothermal environments, like hygrothermal, maybe the moisture absorption things in the seashores for oceanic thermal thermal energy harnessing, and in so many other places wherein the moisture is the threat, we can even use here. So for understanding like how exactly it works, and we can enhance the health of that particular composites and the structures we're using for that kind of environments, wherein the salinity of the ocean and the moisture will affect onto the structural health. So crack propagation can be stopped in the structures due to fatigue and reverse deflection in the beams and structures, and active vibration control in structures and the composites using SMA and PZT materials. So that's what we can achieve here. So this is one of the case studies which we have already done here. So now the different stacking sequence we can see here. The composites what we have developed here, the composite we can see here, the graphene layer we have, and we have the carbon fiber layer, the carbon nanotubes layer, that is the darkest is the carbon nanotubes layer, and here the graphene reinforced FRP composites, that CFRP composites, and here we have SMA. So this is carbon nanotubes coated CFRP composite, first layer. Second layer is graphene coated CFRP composite. Third layer is shape membrane one. So that means it is being sandwiched in a systematic way following the different stacking sequence. Now the first stacking sequence is the U, second stacking sequence is O and T. We have given a different stacking sequence. How exactly it deflects, how exactly it reacts under different stresses, under different radius of curvatures we are getting into it. So that is buckling and post-buckling responses of the smart doubly curved composite shallow shells embedded in SMA fiber under hygrothermal loading. So that's what I told you right now, just in the hygrothermal explanations of it. A composite doubly curved shallow shell has been investigated in different thicknesses and different radius of curvatures. And when it is being sagged, then we are going to, we have studied onto the different levels of stresses which is being generated, and different levels of understanding of different the training parameters and different mechanical parameters. Under the influence of different mechanical parameters, we have investigated on this kind of things. So it's assumed that the first layer consists of the PCF, and second is the PGF. It's what? The polymer carbon nano reinforced fibers. That is the polymer with the graphene reinforced fibers. And third layer is just shape memory alloys with the matrix. That is what matrix was used, was the epoxy 5052 we have used here. So that's what epoxy resin 5052 as the matrix. In that, all these like stacks have been generated, and that laminate has been inspected for different levels. And now we have achieved the temperature, like how exactly this the modulus, elasticity modulus has given a different temperature levels. So that means at different temperature levels, it has given the different elasticity modulus we have achieved here. So that means as the temperature has increased, elasticity modulus has been stabilized. That's what you can say. In the shape memory effect, we have clearly achieved the shape memory effect with the help of the SMA wires, SMA meshing enhancement. So in the recovery stresses also we have achieved here. Now that is with the 3%, 4%, 5% of reinforcements, we have achieved the so-and-so recovery stresses in with the different influence of different temperatures. Similarly, we have a different stacking sequences with the height, the stacking ratio, what we have achieved here. With that stacking ratio, we have achieved the different for different temperature levels and different curvatures from 0 to 2. We have achieved this kind of graphs on it. So that is how it exhibits under the influence of different temperature levels. It has given the reverse stressing formation, and that gives you the clear-cut picture of how the buckling of the re-buckling of the composites can be achieved in that particular levels. Next, second study that we have already done is with the embedment of the SMA wires under some stripe. That's what the CFRP stripe we have made here. And we have subjected this for the 3-point bending. As I've taken an example, by following ASTM standards, we have used, and we have subjected these SMA wires into the carbon fiber composites. At first, 2 layers of the carbon fiber composite, and then we have embedded the different number of SMA wires. That is, the different volume fractions we have gone with. So in this study, we have mounted 1 wire, 3 wire, and 8 wires we have embedded, and then we have investigated like how it behaves, how it is sustaining to the stiffness of that particular composite, and how it is benefited under the 3-point bendings, and how it can retract back under the influence of the mechanical forces and crack propagations. So that's what we have done. As I've told you in earlier, that we have subjected this to 750 degrees Celsius to train it to the original level. That's to make it understand to the original crystal structure. And then we have trained it at different cycles. We have seen the stress strain graph here for the different cycles. For 5 cycles, how it is giving the stress strain graph. For 10 cycles, how much it is giving, 15, 20, 25, 30, 35, 40. So that means we have trained, we have checked whether it is working properly for 40 cycles. And we have seen that very small deterioration we have found from 5 to 40 cycles. So that means it's giving more stability and more repeatability in memorizing the shape and achieving it to original position. So that's what we have achieved. We have observed in this study. So this is what the samples we have seen, and we have studied by mounting the strain gauges onto it. So that is 1 wire mounted. We have mounted 1 wire. Here we have mounted in the second sample. We have mounted 3 wires, and here 8 wires we have mounted. By very calculative and very systematic arrangement of the shape memory alloys wires with different volume fractions. So in that different volume fractions, we have studied that how exactly it gives the stiffness. Because of course we can see that one thing we should understand very carefully when we are using this in the composites, that when we are training this and we are subjecting in the no load conditions, that is simply we are just subjecting it to a heated condition, then it can retract and it can come to some, it memorizes its shape and comes to that particular shape that we have trained for. But what happens when the stiffness is added into it? That is the stiffness of the composites, stiffness of the fibers, stiffness of the matrix matrix we are using there. So these all are accumulated, and for the simple movement, simple twist, it is not possible to achieve the 100% of twist what we have seen in the no load conditions or no embedment condition. So we have to understand that how exactly it makes, because all the composite has to be twisted. So when all the composite has to be twisted, then certainly there should be more strength. So we have inspected this thing, we have investigated by deploying this with the different volume fractions, and we've studied that, yes, with the different volume fractions, as we are using the more number of fibers, it gives you the more stability, more twisting phenomenon can achieve here. And at the different temperature levels, we have seen the stress strain graph from 30 to 65 degrees Celsius. We have seen that it gives a more stability. It gives a more stress sustainability at the different temperature levels. So when we are using a more number of wires, it showed an adverse effect, that it retracted. That means you can say when we have subjected this for the 3-point bending, then certainly it sags here. When it sags, what happens? We are achieving in the thermal chamber, we have done it, and ultimately we are subjecting this for thermal loadings. When it is being thermally agitated, it trains to move in this way. So it trains to move in the hub way. Then what happens? Mechanical forces are acting adverse to it. So that is how makes it to make some kind of like strain restorations on it. So this strain restoration will give more stability into the bendings. So that's how it avoids the bending phenomena into it. So to some level, of course. So that's what we have achieved. And in this, the Martin sighting start at 32 degrees Celsius, which is finishes at 27 degrees Celsius, and austernating starts at 50, and austernating completely finishes at 65 degrees Celsius. That's what we have achieved, and the different modelers for that particular transformation we have achieved here. So that's what the outcomes of the particular beam we have achieved. So that's about the trends and the case studies we have come across with. And I thank you for giving me an opportunity to express my the experience to all the audiences. And this is what the front sheet of our brochures, which we are giving the the research and consultation services into it. So for any kind of queries, any kind of clarifications, people can approach directly to me, and the contact numbers are already given in the front page also, and here also you can see the contact details. You can approach directly by email or by telephonic contacts. Thank you so much, sir.
Yeah, Dr. Basith, thank you very much. Very informative session. I think a lot of information is there about advanced materials, structures, their applications. So really, we are very much fortunate that we are listened your lecture. So even though lecture was little lengthy, but it is not boring. That was still, I think participants are stick to their seats. So now I request Umair Ansari just take the questions, whatever the audience participants have asked.
Yes, there are a number of questions.
Thank you so much, sir. Thanks for your gratification on this. Thank you all for the appraisal on this. Hope the lecture was not boring.
No, lecture not boring. Very informative session.
Online lectures, and as I saw that the clock has already been ticked. It was like when I was in the flow, I just forgot the time sense. Anyways, thank you. Please.
Thank you. Thank you very much.
Yeah, there are a number of questions, sir. You should. One question from shape memory alloys are used for degree of freedom. Is also in robots.
Yeah, of course. All we have to do is for the different degrees of freedoms. All we can do is this materials, this wires, what I have shown the example in the robotic arm end effectors. We have to just train it to that particular direction. I mean, particular shape. So in that particular shape, like whether it to retract, whether it to bend, whether it to make a curvatures, we have to train it to that particular level. So once we are training that wires, we can embed that into the end effectors, and that makes a kind of when it is being, if the wire is being suspended here, it's being embedded here in this first finger, second, third, and fourth, and we want this first finger to make into action, then this wire will be working. As I've told you, the two-way shape memory effect, right? So in that two-way shape memory effect, first will be, first will be for fully closing, and second will be for partial closing and all. And third original will be like this. So in that way, at different temperature levels, all we have to do is ignite some temperature over here. So once we are igniting some temperature here, once we are agitating that temperature on that particular level, then it changes its shape. So that's how the mechanism what we have here. In that we can we can go for the different linkage mechanisms, and we can achieve the different degrees of freedom on that particular thing. So this is just a material characteristic which we have to train it to your application. So we can make it to bend in this way also if you are not making any restrictions here. So finger can be twisted here also as well, because all we are just doing to bend, sag, and hop. So that's what, when we are making the wire to bend in this way, it will bend in this way. When we are making the wire to bend in this way, then it will bend in this way. So that's what it purely depends on the application point of view to go for.
Yes. Sir, another question is any disadvantages of using shape memory alloys?
Disadvantages is, we can say, the characterization cost, the building cost. It's really expensive, I can say. Disadvantage is that only in my view. There is no disadvantage. We cannot say, because of course we are using nickel and titanium, which are very stronger, of course, and it gives the structural stability as well. It gives you the more functionality as well. It gives you the shape memory effect as well. So disadvantages, it's for making, synthesizing, and characterizing the shape memory alloys is itself little expensive. So because we cannot go for the conventional ways of characterizations, we have to go for a little advanced way of characterization. So that's why it is expensive. That's the disadvantage.
Yes. Can this concept of shape memory alloys can be extended to temperature memory alloys in the field of MFCG, food and manufacturing group, sir?
Of course, these are the temperature sensitive alloys, of course.
Yeah.
And this can be extended to any point, we can say, because that is what we are encouraging the research and advancements on this. Currently, these are restricted for the thermal based shape memory alloys and the magnetized shape memory alloys, MSME. So that's what as I have explained, that it is going to get influenced with the temperature difference only, and it changes its shape. So we can activate any mechanism. We can go for any kind of like devising. So we can develop the devices onto it. So whether it is being used for the different mechanical aspects and all, we can generally we can go for it. But the question was not clear actually, because what is that? Can you please repeat it so that I can come back to it?
Can this concept of shape memory alloys can be extended to temperature memory alloys in the field of MFCG?
Exactly, these are the temperature memory alloys itself.
Yeah.
This itself is the temperature memory alloys. That means two-way shape memory effect, what I have told, at two different temperature levels, it is just making it. Of course, the point is, the questionnaire is asking, that at different, like if we have to memorize for the different temperature levels, maybe 5 or 10 temperature levels, for 30 degrees, for 50 degrees, for 70 degrees, 90 degrees, 120 degrees, like that, right? That can also be achieved, but right now we have currently we have investigated to 1-way and 2-way shape memory effect only.
Yeah.
Of course, I feel like with the different the doping mechanisms, with the different substitutional and interstitial mechanism, there may be chances of going for this thing also. Because if you see 3-4 decades before, we were not at all thinking about this. There is something which is called a shape memory effect. Now we have this in our hand. So there are more possible scope of going for the shape memory effect in the different temperature levels as well. So that is what we have to go for. A lot of metallurgical characterizations, metallurgical investigations will lead you to develop the so and so materials, and that can be the new innovations in the field of metallurgical sciences.
Yeah, actually we are running out of time, so maybe we'll take only last one question only. Please take one question only.
Yeah, sure.
Okay. Is the that is question from Kalimullah. Is the market ready to take SMA materials to a broader product range in the future, so as to get rid of use and throw product concept, which is increasing the waste load on the earth and has impact on environment?
Indeed. Already the things are being like taken up into a different application point of views. Of course, this shape memory alloys can be used for the various commercial aspects of it. But the thing, as I have told you, that it is little expensive. It's little expensive right now, and so many like the mechanisms of metallurgical mechanisms we are going with, and characterization mechanisms. Like what happens when the different interstitials, substitutionals, and doping will affect onto that particular material under the influence of the temperature we are just going for. And after that, just a decade before, we have inspected that for, we have inspected and innovated a new class of SMA, that is with the magnetism, with the different alloys. So in the same way, we can develop the materials to go for the further extensive shape memories and all. So, and for the commercial point of view, like of course, it's being open to use in any kind of mechanical devices for the commercial application as well. So these are available commercially available SMS are there. You can just import it from China, or as well as in India also. The people are preparing in the Bangalore CSAR National Aerospace Laboratories are preparing indigenously in India. So most of us are like being taking from either NL or from China. But more innovations, more experimentations and investigations can lead to more applicability that can be more, go for the like commercially enhanced equipments and devices.
So there is a last question. As you discuss about the coating, these bulletproof glasses and bulletproof jackets is come under this only?
This bulletproof jackets, what you have talked about, bulletproof jackets are not coated actually. These bulletproof jackets are made by the high strength fibers, that is Kevlar fibers usually we are using, and we are going to use for some kind of like polymers we are using. So which are highly resistant to the impacts, high velocity impacts. In my studies also, even I have some specimens here which are, I'll show you, just I have in my room itself, as you've told that bulletproof. See, this is the specimen, as you got, fortunately you've got it. If you can see here, this dent, what you can see here, this is the bullet. This is a first degree hybridized Kevlar composite. So that is Kevlar and E-glass with the epoxy 5052 we have taken, and we have tested under high velocity. That is the bullet impact you can see here. And we have tested for different specimens here. Now we can see here, this has not perforated. This has made a dent, but this has not fully perforated. Perforation means it should fully fracture this, the shield, and it should pass through. But here you can see a very light dent it has proven. So that's what the different effects, the impact of bullet impact on the different parameters, that is thickness, compositions, what we say. So that will be very much helpful in going for different high quality bulletproof jackets and all. But for coating perspective, it's completely different. Even in glasses, it's not like coating. Coating is not the parameter for glossy. Even in my glass, this is the Carl's glass. So people say that this is dust proof, waterproof and all, water repellent and all. So coating can make it to be a kind of like, lotus leaf kind of structures. Nano coating will be there. So that is called as the hydrophobic coating, hydrophobic. So it will not make it to, for the moisture depositions, droplet depositions and all. So like that dust deposition can also be like repelled. Dust deposition coating is there. So like that coating can be helpful for that kind of things. Even in the modern cloths are there. That is what is that? Anti-shrinking cloths are there. So these are all like with the help of like carbon particles, carbon nanotubes and nanoparticles we are using, and we are suspending when we are fabricating this cloths in the cloths. So in that level, we can just avoid the moisture absorption and water depositions, dust deposition and all. So that makes a very clean clothing every time. So we need not to wash again and again like that.
Thank you very much, Dr. Basith, Syed Basith. So really wonderful to hear you this lecture. I suggest to participants, because if you share your email address, future if they're having any doubts, they can directly contact you.
Indeed, sir. My email ID is mentioned here. You can just note down my contact number and email ID.
Yeah,
so
please.
Contact me anytime personally.
Yeah, just you tell us so that we can share in the chat box so that
This is my
will
email ID, sbm3.engg@gmail.com. So if you have any kind of questions, any kind of clarifications, or any kind of help, you can just contact me on this email, or you have my telephone number as well. You can use it for contacting me anytime.